you should skip like half the video if you already know some basic physics. Hello, today I'll try explaining induced polarization in geophysics from a physics standpoint, and we'll start with the basics just to make sure we don't miss anything. What does matter consist of? It consists of atoms, right? Atoms consist of also something. They consist of electrons, protons, and neutrons. They're not actually particles, they are wave functions, but for the sake of the discussion, let's call them balls that have certain properties. And let's draw a helium atom. What does helium for? Helium has 2 protons and 2 neutrons and 2 electrons, right? Most likely. As I said, we have electrons, we have protons, and we have neutrons. Neutrons are neutral, they have no charge, they are boring, but electrons are assumed to have a charge of -1, and the protons are assumed to have a charge of +2. Oh my god, what I'm saying, it's +1. What happens if we take 2 electrons and bunch them together in this volume? What is the total charge of this volume? Yes, you're right, Jimbo, it is -2. What is the total charge of this volume, of this helium atom? Let's calculate it. +1, +1, -1, -1, +0, and +0 equals to 0. Yes, this atom is neutral, it doesn't have a charge. But again, it is composed of charged particle, yet the total charge is 0. At least for now. We can make it polarized by removing 1 electron. We just yank it off and we get a total charge of +1. It is what we call an ion. For now, let's talk about interactions between those particles. Let's say we have 2 protons and we have a proton and an electron closer together. Let's say this is volume 1 and this is volume 2. These are not connected. Those are 2 different experiments. They're floating in space and there is nothing else around those 2 protons. Same is down here. Protons will pull away from each other. That's just how it is. We can know the force of this interaction. Q1 is 1 plus 1, Q2 is +1 as well, so it's 1. We just know that those particles pull away from each other. What is happening here? Electron will attract to the proton. Well, it's not an electron. It can be any kind of negative charged particle. It can be a negative ion, an antiproton, anything that is negatively charged. And the proton will do the same. Those elementary particles are not racists. They like diversity, all right? A question for you. What will happen if 2 electrons are close by? Now, we have it out of the way. Now we can talk about polarization. Let's say we have volume that is filled with some metal, with some material that conducts electricity. Again, we'll talk about conduction a little bit later. Some square. And what happens if we place a huge ball of electrons at the left of this volume? Let's say it has 2 to the power of 10 electrons. I don't know how we're holding those together, but let's say we do. And what will happen? Oh no, actually we should talk about conductors and isolators right now instead of talking about that later. All right. We have certain materials in nature. Some are good conductors, some are not so good conductors. What makes a conductor conduct? Again, we have 2 volumes. The first one is some metal, doesn't really matter, and the second one is, I don't know, some rock, whatever. Both of those materials consist of atoms. Atoms consist of electrons, protons, and neutrons. But the key difference is electrons inside of a conductor, such as metal, are free to go. They're not free to leave the conductor, but they are free to travel around. They have no borders inside. They're chill dudes, right? And isolators are, how do I say, they are very isolated. They do not like sharing electrons between themselves. So what happens if I take a conductor and place a negative charge near it? It's quite simple. All the electrons will be disgusted by this huge collection of electrons on the outside, and they will try to bunch up at the other end of the volume. What does it leave us on the left side? Again, remember that I did not add nor subtracted any particles, charges, anything from this volume. It is fully isolated. They interact only through the electric field that is created by this negative charge. Remember what happens when we remove an electron from an atom? It becomes positively charged. It always had this positive charge, but since we removed one negative, the total charge has changed. So we get a lot of positive charges on the left side of this volume. Again, the total charge of this volume is still the same, it's still 0, but we have localities that have higher concentration of certain charge. In this case, right side, and the left side has higher concentrations of positively charged ions, and those charges generate their electric field themselves. Let me draw it. So electric field always starts at the positive charge and ends at the negative. So this is what we have. We have a dipole. We have an electric dipole. An electric dipole is basically the same as a magnet, but instead of generating magnetic field, it generates an electric field. Well, those two are actually the same, but we're not getting into that as well. So what happens to this volume? Again, you see this locality of positively charged ions is closer to this excessive negative charge than this locality. All right, it means that the force of attraction for this area, for this volume, towards this charge will be greater than this force of destruction. Nah, that's not it. Anyway, it attracts, right? I can demonstrate you this. Here's some pieces of paper. Yeah, I hope you can see those. And I'll take, where is it? And I'll take a comb. And I will rub it aggressively against my hairs. And let's see what happens. It starts to attract. Easy? Yeah, pretty easy. Anyway, I know what you're saying. I know what you're thinking. Hold on a second. Those pieces of paper are not conductors. They are paper, and as far as we know, paper is basically a pretty damn great isolator. And yes, I say, you're right. I kinda did bullshitted you here, but let's see what can happen in an isolator. What we just saw was polarization. We induced a polarization in this volume by having an external charge, which created an external electric field. And this electric field polarized this piece of something. Polarization can have different mechanisms. For example, this is polarization in conductors. In isolators, it can be a little bit different. Let's say we have salt atom. And we have, what do we have here? We have let's forget about salt. Nah. Let's just imagine some molecule that has an excessive positive charge on one end and excessive negative charge on the other end. Almost all molecules are polar, like even water is a little bit polar. It basically has a dipole moment. Looks similar, right? And when we have an isolator, just like floating in space, those dipoles can be arranged chaotically, like plus, minus, plus, minus. They're all over the place. But what happens if we introduce an external electric field? This is an electric field. Here we have a huge plate, like surface charge that have a positive charge, and on the right we have some, I don't know, also a plate which has a negative charge. And inside here we have this volume of paper, and this volume of paper has those dipoles. But look at what happens to the dipoles. They rearrange to follow the lines of external electric field. So the negative charge of those molecules will try to face the positive charge of positive plate, like here, and negative side of the molecule will try to face the, oh no, I messed things up, I'm sorry. Yeah, this is the negative plate, this is the positive plate. Positive sides will face the negative plate, and the negative sides, the negative end, will face the positive plate. This is polarization. As I said, polarization can have a lot of different mechanisms, such as, what is important is that when we remove the external electric field, it takes time for those charges to reorient or to recombine in case of the conductor. And we are interested in that time. This is what we can call the time to discharge. So, how do we measure things? How do we do this in practice? Let's say we have a soil, like some field. This is surface, and this is Jimbo. Jimbo wants to measure the IP of this area, let's say. I don't know why Jimbo is floating, but yeah, you can ask him later. And this is the cross section of the field, whatever. We have just some, I don't know, something that looks like this. So we have soil, and we have a volume like this that is something else. Let's say some sulfide, I don't know. What do? We need, first of all, we need to create that external field. Remember? First we have a volume that have no charge. Then we introduce an external electric field that goes through this volume. This volume becomes polarized. The external electric field is still there, but the volume is polar. It's an electric dipole. Then we remove the external electric field, and the volume is still polarized. This is the time when we remove the external electric field. It's still polarized. The charges the charges start moving closer to each other already. They do it immediately as soon as you disable, remove the external electric field. And after some time, it's all back to normal. The homeostasis has been achieved. So we are interested in this time. So what do we need to do first? We need to introduce the external electric field. We do this by connecting a battery. Yeah, usually they use acid batteries in field, but I think this thing will do for now, for us, for our purposes. And we connect. First we place two electrodes. One electron is will be our positively charged electrode, and the other one will be a negatively charged electrode. Yeah, if I will publish this video, I hope Duracell will sponsor me. Anyway, we connect one wire to the negative charge and the other wire through a switch to a positive charge. Yeah, here will be our battery. I'll draw it like this. This is an electrical sign for a chemical element. Nothing happens until we close the switch. Let's close this switch. What happens then? Then an external electric field between those two electrodes is created. So the electric lines will go something like this. And of course the current will flow because soil is usually wet. It can have some salts, minerals, electrolytes, whatever. So we are in this step. Now what happens next? This volume starts getting polarized. Remember, this is our positively charged electrode, and this positively charged electrode attracts electrons in this area. For the sake of this discussion, we will say that they collect at the opposite sides of this volume. Okay, good. We have polarized it. What now? We have to measure it somehow. And in order to do that, we will use a voltmeter. Yeah, let's keep it simple. We also introduce two electrodes in this area. The spacing of electrodes, the materials of the electrodes can be all different. If we want to test deep layers of soil formations, we space electrodes further apart. If we're interested only in shallow measurements, we put them closer together. But it's all beyond the point, because we are interested in the principle itself. What happens when we remove the external field? How do we do it? We do it by opening the switch. What happens then? Our external field disappears. Right? Right. But we still have this dipole. This dipole generates an electric field. Let's call this internal electric field. Positive charges. The lines that represent electric field start on the positive charge and end on the negative charge. And it looks something like this. It basically looks like a magnet. But instead of being magnetic, it's electric. Yeah. And you know what happens when we have electric field lines flowing through a conducting material? Yeah, it creates current. And we can measure this current and voltage. And we can measure this by this voltmeter. Internal electric field, will slowly dissipate. Internal electric field will disappear completely. Let's have a test. I think it's time for the demonstration. All right. So I have this battery. Okay, let's orient like this. And I have prepared sample soils for the demonstration. These are the sample soils. Yeah, those are not sample soils, I know. But those components will model our sample soils. This is a sample that has no chargeability at all. This has a little chargeability, and this has a lot of chargeability. So let's start with no chargeability sample. We are basically doing, what's it called, resistive tomography, electrical. Okay, you know the name better. We connect battery, we connect the battery to the sample, and nothing can, yeah, of course nothing happens because we don't have our multimeter attached. I mean voltmeter. I'll use my oscilloscope for that. It will be much better to show the graphs. All right. I connect plus and ground to our resistor, our soil sample, I mean, and I connect my battery. Let's actually open the switch. See, we have current source, which is basically a battery. That is these two wires, this negative electrode and this positive electrode, and they connect to our sample soil, and we have something that measures the response of this sample soil sample. God damn it. This is the graph. What does this graph show? It shows us the change in voltage. The change in voltage across these 2 points. So I connect the battery. And yeah, nothing exciting. See, I connect. We have basically electricity flowing through the soil. I disconnect. We have no electricity. I connect, disconnect, connect, disconnect, connect, disconnect, connect, disconnect. You see how straight those lines are? They're basically generating a square wave, but it's beyond the point. Anyway, it's boring. Now, look what happens if I change the sample, the soil sample. Don't look at that noise. It's okay. Come on. Come on. Get it. We don't see anything, right? Right, because the switch is closed. What happens if I mean the switch is open. What happens if I close the switch? Yeah, still the same picture, but here's what will be different. You see? When I disconnect, it does not it doesn't reduce to 0 immediately. It still has some internal charge. Let's actually measure this time to discharge. Single trigger. We'll trigger on the yes, connect, and I disconnect. Tick. And we'll use those 2 lines as our ruler. We'll place the first line at the edge and the second line just as it gets close to 0. What do we get? We get 20, well, I mean 200 milliseconds. Let's call it 200 milliseconds. Let's write down this number. T discharge 1 is equal to 200 milliseconds. Right? Yeah, that's already something. Let's change the soil sample for a different one. Okay, this soil sample has the potential to hold way more charge, so it in theory should discharge for a longer time. And let's actually test it. Okay. See, I connect, it's again the same story, but when I disconnect, it's something different. Again, let's measure it. And disconnect. Oh, first line goes to the edge, and second line goes right about as it's getting closer to 0, and we get 70. Let's call it 800 milliseconds time to discharge. 2 is 800 milliseconds, and that's basically it. One more thing though. One more thing. It's just one number, right? Again, we have two numbers because we have two soil samples. One that can hold charge, for example, I don't know, whatever, and something that can hold charge very well, like sulfides. Those are two different soil samples, like far away apart. But how do we get a map? How do we get something more useful? That's simple. We just have this same exact field. That's Jimbo. Don't forget the Jimbo. And we do all kinds of measurements. So we like place two electrodes here, then two here. When we do the measurements in this area, and then we get a number in this point. Well, then what do? We have this. We measure this exact point, but we measure it slightly higher by narrowing the distance between the electrodes, like let's say here and here, right? Those are two new sets of the electrodes. It means that we are measuring our time to discharge in this point, and then we do that with the whole area. Yeah, just a cross section. We can do this for the areas as well, and we get a heat map. At some points we can have a really low value, like let's say 50, 60, 31, I don't know, 100, 201, 250, and this gives us a heat map of chargeability of the field, like where the chargeability is high, we color in, and where it's low, we color in with a different color, whatever. And this allows us to understand what actually lies down there. Again, we do not know the exact chemical composition of this area. It can be anything. It can be a cave, it can be some collapsed ancient temple, it can be sulfides, it can be groundwaters with certain chemicals. We do not know the actual composition, but we can derive it from tables, from people who already did their research, who know that, like for example, sulfides have time to discharge. I don't know. I'm just saying the arbitrary number. Like sulfides can have their time to discharge in between 340 milliseconds, and I don't know, some nickel or I don't know, has lower time to discharge, like 100, between 200 milliseconds. And looking at those tables and our heat map, and also at other secondary properties, we can predict what lies down beneath. It's a little bit more difficult than that. We still have to do some math on this heat field in order to receive the an actual like volumetric map of chargeability. But in essence, that is it. In essence, that's how induced polarization, method of measuring induced polarization, works. You have an external electric field, which is generated by a battery, because it's the most convenient way to generate external electric field. And we have a certain mass, volume, rock, whatever, cavity, that can be polarized. Again, how polarization works, we talked about. And then we polarize, charge this volume of space, and abruptly, the key word is abruptly, remove the external electric field, giving our instrument a chance to measure the internal electric field of this boulder, whatever. We can say what kind of mineral is down there. There are different ways to measure this time to discharge. It looks like something like this, right? So at first, no battery is connected. So it means no external electric field. Then it suddenly rises because we hit the switch, and it stays relatively the same. Here we are measuring our battery's electric field. This is not what we're interested in. And then when we suddenly disconnect the external electric field, our soil holds on to the charge for quite some time. And we are interested in, usually, in this time period.